Hello, everybody. Today we are going to very briefly introduce the idea of complex numbers and just look at the curriculum that IB has for complex numbers with the intentions of taking some time after we're done integral calculus to give the higher level topics a closer look, some chances to look at them more in depthly while the standard level students are writing the paper one, paper twos. So here we go. Complex numbers. What is a complex number? Complex numbers are the combination of real numbers and imaginary numbers. And the imaginary number is denoted with the symbol I. And what I is, it is the square root of -1. Okay, so we should hopefully be familiar with our real numbers, right? Our real numbers are basically the number group that makes up everything that we're used to. So positive numbers, negative numbers, decimals, fractions, numbers like pi or the square root of 2. These are all real numbers. So complex numbers fall outside of that category, and then the kind of the bigger umbrella that contains all of these numbers, real numbers and imaginary numbers, we call that complex numbers. So why do we care about complex numbers? Well, the best analogy or the best example I heard is, well, the same reason we care about negative numbers, right? What is a negative number? If you think about it, it really doesn't mean much, right? And it's really just denoting the opposite of a positive. So, for example, I can gain 30 of something, or I can lose 30 of something, right? But the idea is it's still 30. It's just one's gaining, one's losing. So the concept of a negative is really just the opposite of a positive. Think about it in terms of physics, right? If we were doing displacement, a positive 30 might be a displacement in the eastern direction, and a negative 30 just might be displacement in the western direction, right? So it's just pairs, right? That's all negative and positives to help us define pairs of groups. Well, complex numbers just gives us another layer on top of that. Complex versus real, positive versus negative. So now instead of defining pairs, we can define groups of 4. Right? A couple of things to note about I. So I squared is equal to -1. Right? And that makes sense because if I is equal to the square root of -1, then we have the square root of -1 squared, right? And that is equal to -1. And then I to the 3 is equal to I squared times I. Well, we just said that I squared is equal to -1. So I to the 3 is equal to -I. And then I to the 4th is equal to I squared times I squared, which would be -1 times -1, which is equal to 1. And then this pattern just resets. So I to the 5 would be equal to I to the 6 would be equal to I squared, which is -1, and so on and so on. So the pattern just kind of loops around. Okay? So because complex numbers are thought of in terms of their real and their imaginary components, we write that way as well. We would write a complex number z as a plus bi, where a is the real component of our complex number and b is the imaginary component of our complex number. Right, so we can represent complex numbers in terms of their real and their imaginary components. So, for example, the complex number 3 plus 4i would have a real component of 3 and a imaginary component of 4. And we can add and subtract. We can do operations with complex numbers in much the same way that we would do operations with variables. So, for example, if I had complex number z equals 3 plus 4i, like the one we had in the previous example, and complex number w is 2 minus I, for example, then I could do z plus w, right, by doing 3 plus 4i plus 2 minus I, and then we would just add our imaginary and real components individually. So this becomes 3 plus 2 plus 4i minus I, or 5 plus 3i, right? And subtraction would work much the same way. We could also multiply and divide complex numbers as well. So, for example, if I wanted to take complex number z here, 3 plus 4i, and multiply it by, say, 3. So 3z would be 3 times 3 plus 4i. And we could just distribute that multiplication like we would usually. So we can take that 3 and multiply it in. So 3 times 3 is 9, and 3 times 4 is 12. 12i. We could also take z and multiply it by a complex number, or an imaginary number. So, for example, 2i times z would be 2i times 3 plus 4i. And again, we would expand this by multiplying the 2i in. So 2i times 3 is 6i, and 2i times 4i is 8i squared. Right, and as we just talked about, I squared is actually equal to negative 1, so this becomes 6i plus 8 times negative 1, or negative 8 plus 6i. And I could even go as far as multiplying z by w, right? So 3 plus 4i multiplied by 2 minus I. And again, we are going to expand this much the same way that we would expand if we were multiplying binomials. So 3 times 2 minus, plus, I guess, 3 times negative I plus 4i times 2 plus 4i times negative I, right? So 3 times 2 is 6, and 3 times negative I is negative 3i. 4i times 2 is 8i, and 4i times negative I is 4 times negative I. Well, sorry, let's do negative 4. Negative 4 times I squared. Right, so we get 6 minus 3i plus 8i plus, so again, I squared is negative 1, so negative 4 times negative 1 is positive 4. And again, we can combine our real and our imaginary components here. So 6 plus 4 is 10, and negative 3i plus 8i is 5i. And there we go. So when it comes to dividing complex numbers, it gets slightly more difficult, but we can just use the tools that we're used to. So if I take my 3 plus 4i and I divide it by 2 minus I, the problem here is, well, how do we do this division? And what we're going to want to do is we're going to want to turn this 2 minus I into a real component, right? Because then we can take each of these things and not have to deal with this binomial, but deal with it as kind of one thing. So we're going to do that by multiplying it by its conjugate. And the conjugate for imaginary numbers is denoted with a little star. So the conjugate of z would be like this, is 3 minus 4i. So the conjugate changes the sign of the imaginary component. So conjugate changes the sign of the imaginary component of our complex number. Component. There we go. So if I wanted to do this, what I'm going to want to do is I'm going to want to multiply w by its conjugate, but also multiply z by the conjugate of w as well. So we're going to multiply this by 2 plus I over 2 plus I. Okay, so then we will expand and simplify, right? So we get 3 times 2 is 6, and 3 times I is 3i. 4i times 2 is 8i, and 4i times I is 4i squared. And I'm running out of room here, so I'm going to go ahead and just erase this part right here. Oh, I guess I can just slide it down. That's the magic of technology, is I don't have to erase. I can actually move my writing. It's a miracle. All right, and then we're going to do the same thing to the bottom. And again, this is the difference of squares. So we get 2 squared minus I squared. All right, so we're going to simplify this a little bit. So we get 6 plus, well, I'll even simplify it further here. We know that I squared is negative 1. So 4 times negative 1 is negative 4. So 6 plus negative 4 is 2. And 3i plus 8i is 11i. And 2 squared is 4, and the square I squared is negative 1, so plus 1. So we get 2 plus 11i over 5. And that's it. We could take this and look at the real component, which is 2 over 5, and the imaginary component, which is 11 over 5i. I, right? And we could break it up into two fractions. Right, so here we are, 2 over 5 and 11 over 5. I is the real and the imaginary component of this complex number. So because complex numbers are broken up into their real and imaginary component, what that means, it can be very useful to represent this on what we call the complex plane. Right, so we would take the kind of two-axis plane that we're used to, and we would break it up into its real and imaginary components on this similar xy axis that we would be used to. So again, if I keep looking at this z equals 3 plus 4i example, right, the way that we would represent this graphically is by going on my real axis over to the 3 and on my imaginary axis up to the 4, and we would see that the point, this is z. Okay? And then what we can do from this is we can look at representing these complex numbers in different ways. So first off, what we can do is we can look at the modulus. The modulus. Okay, and the modulus of our complex number is kind of like its magnitude, right? If we were thinking about it in terms of vectors or trigonometry, right, it's the magnitude of this vector that would make this complex number. So the way that we'd find them, and its notation is the same way. It's used those vertical brackets, right? So we would find the modulus of 4 plus 3i by looking at the right angle triangle that has those dimensions. So the dimension 4 and 3, and the dimension of its hypotenuse is that modulus of z. Right, so that is going to be equal to the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5 in this case. So there are a variety of forms in which we can represent these complex numbers. So the first one we've talked about is the Cartesian form, Cartesian, right, and that's our z equals a plus bi. But we also have what we call the polar form, which could also be known as the modulus argument form, and that is written as z equals r cos theta plus I sine theta, okay, where r is the modulus and theta is the argument. Or we have what's called Euler's form, right? Euler being that special E character, which is z equals r times e to the I theta. And again, the r would be the modulus, and theta would be the argument in this case. So here we go. Let's take a look at how we do this. So if I have my point z, which again is 3 plus 4i in its Cartesian form, and I want to convert that to the polar form, what I would do is I would use a bit of trigonometry here, right? I would use what we know about trigonometry to find that. So again, 1, 2, 3, 1, 2, 3, 4, right? We know the point is here. That is my point z, right? So what we're doing is we're finding this angle theta, right? In order to find my argument, and we would find the length of the modulus, r, in order to find my modulus. So in order to write this in polar form, right, the first thing that we have to do is we have to find r, right? And we already know that r is, oops, did I write those backwards? 3 plus 4i. Is that always 3 plus 4i? Yeah, 3 plus 4i. So we'd find r by doing 3 squared, the square root of 3 squared plus 4 squared. So we get an r of 5. And then to find theta, what we'd want to do is we would want to use a little bit of trigonometry. So theta is going to be equal to the inverse tan of my imaginary component over my real component, right? So in general, my argument theta is going to be equal to the inverse tan of b over a, right? My imaginary component over my real component. So if I grab a calculator at this point, so let me just pull one up here, right? We can do in radians. So these are always going to be in radians. So we have to make sure that our calculator is in radians. So let's do that. So we have 4 over 3. And we do the inverse tan of that. Oh. There we go. Okay. And we see here that theta is 0.927. So 0.927. Right, so the way that we would write our complex number in the polar form here is 5 cosine of 0.927 plus I sine 0.927. And there we go. So there's my coordinate in the polar form. You sometimes see this also written like this, 5 CIS, right? Cosine imaginary sine, and then 0.927, right? This notation is okay because the angle theta here is going to be the same for both of them, okay? Now the Euler's form is quite interesting. The reason Euler's form is quite interesting has to do with the special properties of this character, E. So E is this thing that it just occurs naturally. When we start talking about exponential growth, we see it pop up. We see it in a lot of different forms, and it kind of appears a lot. And hence why we refer to log base E as the natural logarithm, right? And one of the forms in which we see the E appear is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus ... on forever. And if I were to kind of look at this a little bit further, why are these two 1s here? Well, this is 1 factorial and 0 factorial, right? So we get 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial and so on and so on. If I were to add all these up, what I get eventually is E, right? And even more specifically, if I were to look at e to the x, which is quite interesting as well, I get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on and so on. Okay? So if I were to think about this in terms of imaginary numbers, well, what would happen if I put an I in? What if I put it as e to the ix? Well, if we follow the same form as previously, what we would end up getting is 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4 over 4 factorial, and so on and so on. And then if I were to simplify all of these, something interesting starts happening. I start seeing that half of it basically ends up being real and half of it ends up being imaginary, right? So 1 is real, ix is imaginary, ix squared ends up being real because I squared is negative 1, right? So this ends up being negative x squared over 2 factorial, right? And then I to the 4th is equal to positive 1, so this ends up being x over 4 factorial, and so on and so on. And then the imaginary component also happens. So I have I times x plus I cubed is equal to negative I, so this is negative I x cubed over 3 factorial, right? And then I to the 5th would be I, and so on and so on. So, and that would go on forever. Okay? And this is where the miraculous, the beautiful thing ends up happening, is we have something called Taylor series. And what Taylor series is, it actually defines sine and cosine in a very much a similar form. Taylor series says that the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial plus and so on and so on. And sine x is equal to x plus, minus, x cubed over 3 factorial plus x to the 5 over 5 factorial. And if we look at these two forms that we had previously, right, what we might e to the ix was broken up into, well, there is cos x, and there is I times sine x. So what that means is that e to the ix is actually equal to cos x plus I sine x. So finally, if I want to take my complex number z, right, the one that we've been talking about, the 3 plus 4i, and I want to write this in Euler form, right, what we again need to do is we need to think about its position, right, on my complex plane, right? So 1, 2, 3, 1, 2, 3, 4. It's here, right? We need to think about the triangle, the right angle triangle that makes this with 4 and 3 as its side length, right? We need to find the modulus of z, right? And we do that by finding 3 squared plus 4 squared, which is equal to 5. We find the argument of z, which again was 0. I'll find it back here, 927, right? 927. And the nice thing is, in terms of using Euler's form, there's no more work than if we were to use polar form, right? Because, right, we just proved, or we've shown that here it is, right? The Euler's form and my complex form are basically the same thing, right? So what I can do now is I can write z in terms of r e to the I theta, or in this case 5 times e to the I times 0.927. So there we go. There's our Euler's form. So I guess the question now is, like, why do I care about Euler's form or polar form? Well, something interesting happens, right? We start thinking about it in terms of Euler's form. So for example, if I had a complex number z, right? Whatever z is, so it's some a plus b I, and I wanted to square that, right? If I wanted to do z squared, well, that wouldn't be too bad. We could do a plus bi squared, and we would just expand that, right? We would get a squared plus 2ab plus bi squared, and then we know that I squared is equal to -1, right? So, but there's a bit of work involved there, right? We could do it, but there's a bit of work involved there. If I think about a complex number in terms of Euler form, so z equaling r e, that's not where the e goes, r e to the I theta, and I were to put that to the power 2, for example, so z squared equaling r to the ei theta squared, it becomes much easier to square this, right? Because what we can do here is we can write this as r squared and e to the 2i theta. And then I could even kind of take this one step further and think about it in terms of my polar coordinates, right? So z squared would be equal to r squared times cos of 2 theta plus I sine 2 theta. And what that means is that in general, if I want to put a complex number to any power, so z to the n, for example, I can write that in polar form as, or Euler's form, r to the n times e to the n I theta, or I could write that in polar form as r to the n times the cosine of n theta plus I sine n theta. And what we refer to this as is de Moivre's theorem. Okay? It's a nice simplified way in order to take the power of a complex number. So for example, right, if I wanted to do z equals, we'll come back to our 3 plus 4i, but I want to find z to the fourth power, for example. Well, again, what we could do is we could do 3 plus 4i, and we could write that to the power 4, and then we could write that as 4 binomials, and we could expand those binomials. It would just take a fairly long amount of time, right? It wouldn't be a short amount of time. It would take us a bit to get to that final answer. So instead, what I could do is I could write my z in terms of its polar form, right? So we've done that, 5 cosine of 0.927 plus I sine of 0.927. And now I can use de Moivre's theorem in order to write this as 5. So if I wanted to find z to the 4, it becomes 5 to the 4 times the cosine of 4 times 0.927, right? Plus I sine of 4 times 0.927. And there we go, right? We could simplify this a little bit by doing out these multiplications and powers and stuff. So for example, 5 to the 4 is 625, and 0.927 times 4 is 3.709. $3.71. And then I sine of 3.71. And we could even rewrite this a little bit, because 3.71 is somewhere around here, right? It's a bit more than pi radians. So because we know that, we could rewrite this, right? We could subtract pi from both of these and then just make sure they're both negative in that case. If we wanted to. Again, it comes back to what we've learned about trigonometry in the past. But here we go. There's our answer to our z to the fourth, right? So the de Moivre's theorem makes this process of taking a power of a complex number much, much, much simpler. So what we could do now is we can, in fact, extend the de Moivre's theorem to make not just powers simpler, but products and divisions simpler as well. The way that we would do that is we would just consider the same idea that we did previously, right? If I wanted some number z1 being equal to r1 e to the I theta 1, and some number z2 being equal not squared, sorry, but z2 being equal to r2 e to the I theta 2, right? If I wanted to do z1 times z2, right, or in other words, r1 e to the I theta 1 times r2 e to the I theta 2, right, what ends up happening here is this is just a string of multiplication, so we can do this as r1 times r2, right, and then that's going to be multiplied by e to the I theta 1 times e to the I theta 2, or e to the I theta 1 plus theta 2. And the same thing is true for division. So if I wanted to do z1 divided by z2, right, we would get much the same thing as here. We would get r1 e to the I theta 1 divided by r2 e to the I theta 2, right? And again, we could simplify this as r1 over r2, and then e to the I theta 1 minus theta 2. Right, so what that means is now, instead of, again, going through this process of actually trying to multiply or divide these things, we can use de Moivre's theorem to simplify that, right? So if I went back to my z and my w from the beginning of the video, so 3 plus 4i and 2 minus I, right, what I could do, as long as I knew them in terms of their Euler or polar coordinates, I could use de Moivre's theorem to solve that. So just a reminder that z, in terms of its polar coordinate, was 5 cis 0.972. W we haven't done yet, so we could find the modulus of w, right, as the square root of 2 squared plus -1 squared, right, which is the square root of 4 plus 1, which is root 5, right, and the argument of w is going to be equal to the inverse tan of the imaginary part of w, which is -1 over 2. Right, so if I do that, if I do trigonometry, let's do 1 over 2, and then we'll take the inverse sign. We get -0.463, so theta is equal to -0.463, right? So w, in terms of its polar coordinate, polar form, is root 5 cis -0.463. Okay, so now if I wanted to do z times w, right, instead of multiplying and expanding and then combining like terms, I could write this as r1 times r2, and then the cosine of theta 1 plus theta 2. So 0.972 plus -0.463, and we get cos 0.509. And plus I sine 0.509. And there we go. There's our answer, right? If I wanted to divide z and w, and again, what I'd end up here with, I could do it by finding the conjugate of w, multiplying the top and the bottom by the conjugate, expanding, simplifying, going through that whole process like we did previously, or I could do it with de Moivre's theorem and do r1 divided by r2, and then the cosine of r1 minus r2, so we get 972 minus a -0.463, and we get the cosine of 1.44 plus I sine 1.44. And we could even rationalize this at that point, right? So 5 root 5 over 5 is equal to root 5 times the cosine of 1.44 plus I sine 1.44. Okay, so just so this video doesn't go on forever, let's finally talk about the last use of complex numbers that IB would expect of you, and that is factoring what would previously have been unfactorable. So for example, we know that if I would like to factor x squared minus y squared, then we could write that as x plus y times x minus y, right? We would call that a difference of squares. What complex numbers allow us to do is they allow us to factor something that previously would have been unfactorable. So for example, x squared plus y squared, right? So how would I factor something like this? Well, what we can do is, again, we can use the fact that the square root of -1 is equal to I, and what that means is that I squared is equal to -1. Sorry, my brain's not working there for a second. So we could rewrite this as x squared minus I y squared, right? Knowing that when I square I get -1, and then the negative of -1 is +1. So now what this does is it takes a sum of squares and it actually turns it into a difference of squares. So I can still factor this thing as x plus iy and x minus iy. Okay, so what that means is now I have the ability to factor something that would have not been factorable before now by thinking about it in terms of complex numbers. So for example, if I wanted to factor the polynomial x to the fourth plus 10x squared plus 9, right? So what we'll find is that this thing, if we were to just think about it in terms of real numbers, there are no real numbers in which this thing is equal to 0, right? So it actually is not factorable, not completely at least. Now, we can start off by factoring this thing by letting x squared equal u, and then this becomes u squared plus 10u plus 9, and this is a simple trinomial that we have factored previously, right? We get u plus 9 and u plus 1, right? So I can come back up here and put x squared back in the place of u, and I get x squared plus 9 and x squared plus 1. And at this point we would be done because x squared plus 9, x squared plus 1 is not factorable. But again, now that we have complex numbers, we can actually factor this thing if we're thinking in terms of imaginary numbers. And the way that we would do that is just like a difference of squares, except we have to think about that I being there. So x squared plus 9 becomes x plus 3i and x minus 3i, and x squared plus 1 becomes x plus I and x minus I. Okay, so that's it for this video. I think it's gone on long enough. I find it hard to watch an instructional video for this period of time, but hopefully you guys are able to get through most of it. Ideally, what will happen is when we get back from the break, I can help you guys out with any questions. We can go over some practice problems. I have the higher level textbook in the class, so I'd be happy to share some questions with you to try out. And then, like I said, in April, we'll have a chance to kind of sit down and maybe go over this a little bit more in depthly. All right, so enjoy your break, and I will see you guys all when we get back.